Welcome to the world! Hello, ladies and gentlemen. You are with Smile Musa TV. Let's do one thing at a time. You can enjoy here math, crypto, travel, and songs, of course. Bye-bye. Okay, welcome back to Smile Musa TV. Today, we shall have a continuation of our lesson in mathematics in the modern world. However, we shall concentrate in this lesson about computing truth table. Okay? So in the previous video, we have logic statements and quantifiers. So we will now delve into determining whether these propositions or assertions or statements true or false. And we will be building a truth table. Okay? Before going further, let's have some definition of terms. Okay, so an assertion is a statement. A proposition is a statement or declarative sentence which is true or false, no, but not both. Okay, so take note of that, class. Now, a proposition is true when we assign the truth value true, no? So if a proposition is true, we will be assigning the truth value true to it. Otherwise, if a proposition is false, then we assign the truth value false to it. Of course, we will not anymore write the word true, but instead we simply write T, and false, instead of false, we say F. Okay, that will be our convention. Now, before going further, let us have some examples of propositions and whether these propositions are true or false. Okay, so the following are examples of propositions. Propositions. The first one is 10 is greater than 11. Of course, that's false. The billion prime minister, the billion prime rather. Now, when written in base 10, ends in 3. So far, I don't know whether we have we have reached that prime. So it's false. No? All men are mortals. That's also true, no? Because we are human being and we are reaching that. 2 is a prime number. Of course, that is also true. Okay? Now, as I said, no, what is the highest prime number so far we know? Let's have some trivia. Okay, so the largest known prime number, not prime minister, but prime number. A number is divisible by itself and 2. Okay, so the number divisible by itself and 1. Okay, that's a prime number. No, I'm really sorry. It's a number that is divisible by itself and 1. The first example is the first prime number is 2. Yan, that's in my mind earlier. But the largest known prime number as of September 2022 is this one, no? 2 raised to 82,589,933 minus 1. Okay? So basically since the that's the number, no? So a prime number is a positive integer excluding 1 with no divisor other than 1 and itself. So according to Euclid's theorem, there are infinitely many prime numbers. So there is no largest prime number. Okay. Now, the following are non-examples of proposition. So they are not proposition. And why are they not proposition? Of course, the first one is x is less than y. So there's no way to determine whether that is true or not. Number 2, factor x squared plus 2x plus y. That is not a statement, That is a command. Number 3, x is equals to 10. That is an equation, but, well, it's not a proposition. Okay, x equals to 10. How old are you? How old are you? That is a question. So it's not a proposition. Okay. Now, decide whether the following are propositions or not. Anyone? Okay, let's have the first one. 29 is equal to z. Of course, that's not a proposition. Uh, 12 minus 7 equals 5. Of course, it's a proposition. Very good. How about 18 is greater than 5? That's an inequality. Of course, it's a fact that 18 is greater than 5. It's a proposition. How about all women are mammals? All women are mammals. Well, you're correct. It's a proposition. How about where do you live? Again, that's a question. So that is not a proposition. Okay, very good. So let's proceed further. Now, we shall discuss about, in mathematics, in symbolic logic, we instead of we write the sentence, we convert that into a propositional variable. Now, the common practice is we denoted PQR. No? This denotes an arbitrary proposition with an unspecified truth value. So in other words, that PQR, it's a propositional variable, so we do not know the truth value. Therefore, we assign truth value for it. You follow? We assign truth value. Okay, so a propositional variable is a variable that represents a proposition. So in other words, this PQR is actually a proposition, but we don't know the proposition. So it's a representations of proposition. We call it propositional variable. And the truth value is unspecified. So therefore, we assign truth value. Okay, let's have some practice. Okay. Now, the definition is we say, given two propositional variables P and Q, these two propositional variables may be combined to form a new one. So, if you have a propositional P and another one is Q, you can combine it. Just like in English, you can come up with complex sentence. So, with symbolic logic, no, we can combine two simple proposition into a compound proposition, which is now again a new proposition. And the following are some of our operators, or we call it the logical connectives. We have and, or not. Okay. Now, as I said earlier, our concentration today is making a truth table. Okay. A truth table is actually a breakdown, no, of a logic function by listing all possible values the function can attain. So I'm saying earlier that a propositional variable, we can assign truth value to it. Okay? So such a table typically representing the logical variables, no? And combinations in increasing complexity leading up to the final function. We said earlier, if we have P and Q as individual proposition, we can come up with a new proposition which is a seemingly complex one, which is obtained by combining the two propositions are P and Q. Okay, so we can come up with a truth tables. A truth table class is simply a device that is it allows us to analyze and compare compound logic statements. Okay, so for example, a single proposition P. So we can come up with a truth table for it. Now, of course, a single proposition has we can assign only two truth value. It's either true, no? It's either true, it's either true or false. Then of course, we know for the fact that the negation of true is false and the negation of false is true. So in other words, each proposition can be assigned with two, no, with two truth value. It's either true or false. Okay? Welcome back to Ispan Musa TV. Right. Okay, let's proceed further. Now, consider the symbolic statement P or Q. P or not Q rather. So whether this statement is true or false depends, no? Depends upon whether its variable parts are true or false, as well as on the behavior of the or connective and the negation operator. That's how we determine the truth value of a new proposition. Later, we will make a truth table for this statement. Now, a truth table class for this statement will take into account every possible combination of the variables being true or false. Again, for P, we can assign truth value. No? So, per single sentence, per single statement, a single proposition, we have two possible uh, truth value, which is true or false. So, in this case, since it's P and Q, then we expect, according to probability, we can have four possible orders. Okay. Now, by the way, some other books, no, some other books represent the negation of P as this symbol. Okay, instead of the tilde earlier. Okay. Just a recall, there are three possible new propositions that we can come up. No, if we have proposition P and Q. So we have conjunction of P and Q, disjunction of P and Q. We have also negation of P, which is not P or denoted by the not P symbol there. Okay. Then we can have truth tables. No, the truth tables for not P is given. No, so we have only two possible truth value of P, true or false. Therefore, the negation is also the opposite. Okay. So the truth value of uh the truth value of okay, as you notice, the truth value of P is true, its negation is false. The truth value of P is false, its negation is true. Okay, do you get me? Okay, very good. Now let's continue. If we have PQ, okay, we have P and Q. So there are four possible combinations. No? So the usual practice is we write, yeah, we write, okay. So we say we always start no with P, then Q. So in this case, since there are two propositions P and Q, accordingly, to determine the number of possible combinations, we use the formula 2 raised to n, where n is the number of independent proposition. So in this case, there are two propositions. 2 raised to 2 is 4. So we have 4 possible combinations. Okay. So the best practice is, or the best strategy is, since there are 4 possible, so we have 2 true and 2 false. So we have true, true, false, false for P. Then for Q, we can always begin with true or you can start with false, but I will suggest you write true. Then next is false, then next is true, then next is false. So you notice these are unique, no, orders. Okay? Then for conjunction, disjunction, and negation. So you have to go back to the definition of what is a conjunction of P and Q and what is a disjunction of P and Q. Accordingly, a conjunction class is a new compound proposition. It's a new proposition. It's a compound one because it's a combination of P and Q, and they are joined by the words N, and that symbol of inverted V will be our symbol. Now, a conjunction of P and Q is said to be true if both statements are true. If both P and Q are true. So, as you notice, no? As you notice, true, true will give you true. So it must be both. So if one of them are false, then automatically the conjunction is false. On the other hand, for a disjunction of P and Q, no, so we use this regular V but a bigger size, no, P or Q, then at least one of the independent proposition is true, the disjunction is true. So we have true, true, it gives us true. True, false, at least one man. So we have true. False, true, so true. False, false, of course. There's no true there, so it's false. Okay, you follow? Very good. Note, you have to note that this is truth table. There is only one row in which the statement P and Q is true. Ah, this is the row where P is true and Q is true. This conforms to our earlier observations that the only situation which the which the conjunction is true is in the case in which both of the component propositions are true. Again, in terms of disjunction, you can also see that uh, this is the row. The statement P or Q is false when the row no when both are P and Q are false. Okay, take note of that. No, that's our observation. I hope you follow. Okay. Now, however, class, let me differentiate between inclusive disjunction as well as exclusive disjunction. Okay. So there are authors who define these two are different. No? So we have the inclusive and the exclusive disjunction. The definition is very clear. When you say inclusive disjunction, that's denoted by our commons P or Q, is true when either or both of the disjuncts. No? So the disjuncts are each statement, each proposition. We call them disjunct. Okay. So it requires, at least one. If at least one or both, is true, so that disjunction is true. While exclusive disjunction, yeah, is denoted by P bar, no, the P bar V Q, is true when and only one of the disjunct is true and the other is false. So it must be one is true, the other is false. So that's the time that the exclusive disjunction becomes true. Okay. So I hope it's clear, no? You see the difference, You see the difference, class. Okay? So you see. So true, true. Conjunction, disjunction inclusive, it's true. Disjunction exclusive, it's false. No? Why? Because both are true. It must be one is true, the other one is false for an exclusive disjunction. So while the second row, so one is true, that's true for inclusive, that is also true for exclusive. Uh, the P is false, Q is true, so 1 is true. Therefore, that is true for inclusive, that is also true for exclusive. Of course, false, false, that becomes false for inclusive and false for exclusive disjunction. So basically, class, the difference is here, no? Because in the inclusive, that's okay for both to be true. But for exclusive, one must be true and the other one must be false. So in this case, it's still false. Okay. So we have to take note of that. Uh, let's have another definition. Okay. The proposition P implies Q is denoted by that P arrow to the right Q is called an implication. Uh, So it's an implication. And we know if the conclusion is true, regardless of the premises, the implication is always true. Now, take note of that. If the conclusion is true, regardless of the premise. the implication is always true. Or shall we say, if somebody promise you that he will give you a gift on your birthday, so when your birthday comes, he gives you a gift, that is true. But he gives you a gift, your birthday did not come, that's still true. Because we say, if the conclusion is true, regardless of the premise, the implication is always true. So we say the operand P is called the hypothesis. And or sometimes you call it the premise, or sometimes you call it the antecedent. While the operand Q is called the conclusion or the consequence. So when do we say the conclusion to be true? If the conclusion is true, the implication is true, irregardless of the premise or the hypothesis or the antecedent. Okay. So look into the truth table. We can construct this way. Yeah. So you see, PQ. So we have the implication P implies Q. So this become false only when the conclusion is false and the premise is true. You follow? Okay, very good. Huh? So that's clear. Okay. So we have the following also definition. Given the implication P implies Q, so let's talk about the converse, the inverse, and the contrapositive. Okay. Ah, so we have the following, no? So I want you to take note of the definition of the inverse, the converse, and the contrapositive. So we have the operand P and the operand Q. What is the operand P? We call it the hypothesis, the premise, or the antecedent. What is Q? We say the conclusion or the consequence. Take note. When we talk of converse, we we transfer, no? So the conclusion becomes the hypothesis. So instead of P implies Q, we say Q implies P. So that is converse. While the inverse is we negate both P and Q. So P implies Q. The inverse is not P implies not Q. While the contrapositive is we negate both statement and we also uh, make the conclusion as the hypothesis. So instead of not P implies not Q, we say not Q implies not P. Okay. So please look into the truth value. So again, we have PQ. So since we have PQ, no, since we have PQ, so we have four possible combination. In this case, we write FFTT. That's okay. FFTT. So we have FTFT. Okay. So four unique orders. Now, P implies Q. We say it's false only when the conclusion is false. Okay. And the premise is true. Okay. So that's why this is false here. Here, true, true, true. Okay. Now, the inverse. So we negate kasi we negate eh. So the negation of false is true while not Q is false. So true implies true is true. So this is only the case where it's false. Why? Because the not P here is true, which is implies to not false. Which is false rather, no? Which is the not Q. So true implies false. It gives you false. Okay. While the Q implies phi or the inverse, which is we simply transpose the conclusions to be the premise. So it's false implies false, you get true. True implies false, you get false. So it happened here. Okay? So Q, which implies false, which is false. True implies false, so it's false. Then we have also the negation. Okay? So meaning we negate not we negate the P and the Q. We negate the Q and not P. We call this the contrapositive. Okay? You follow? The contrapositive, meaning if this is false, the negation is true. If this is false, the negation is true. So true implies true, so we got true. Okay? If this is true, the negation is false. If this is false, the negation is true, so we got true. So only in this case it becomes false. Why? The negation of false is true and the negation of true is false. So the negation of false true implies false. No, it's give us false. I hope it's clear. Okay? So another definitions that we have to take note, class, is what we call biconditional proposition, and is expressed by a linguistically by preceding either component if and only if. And the truth table for biconditional proposition forms symbolized by P, uh, if and only if Q is shown below. Okay? So a biconditional class is a type of proposition form that is true only when both its components have the same truth value. So it must be the same truth value for P and Q. Okay? So try to see, class. False implies false. Now, both are the same value. Therefore, it's true. False implies true. One value is different, so it's false. True, false, that's false. True, true, it's true. So it must be both, must be of the same truth value for it to be true. Clear ba? Okay, very good. So, allow me to introduce, no, to make you clearer of how to make a truth value. Consider the following basic rules for constructing a truth table for a compound statement. Okay, you can just read it, no? So for a two variable, no? For a two variable, okay? So the number of rows in the truth table depends upon the number of basic variables in the compound statement. To determine the number of rows required, count the number of basic variables in the statement, but don't recount multiple occurrence of a variable. So meaning to say, you don't count the negative as different from a statement. Okay? So we simply count the positive or the propositional independent proposition. Okay? We don't count its negation. Okay? So for a two variables, so we shall have four rows. Okay? For a three variables, so we shall have eight rows. And try to see the possible combinations. Yeah? So we have there 4 true, 4 false. So in here we have 2 true, 2 false. Then 2 true, then 2 false. So it's a unique combination. You try to observe. And of course we can have true, false, true, false, true, false, true, false. So that's PQR, no? For 3 independent variables, there must be 8 possible rows. Okay. Now, how do we indicate the number of columns? How many columns are we going to make? As we said, the number of independent propositions define the number of columns. So basically, per independent proposition, one column. And the number of rows depends on the proposition, which is 2 raised to n power. So, example, you have 3 independent proposition, PQR. So, 2 raised to 3 is 8. So, that's why we have 8 rows. But how many columns? Now, it also depends on the logical connectives. No, depends upon the number of logical connectives in the statement. The following are guidelines. You can just read. No, okay. We have the following. So, example: make a truth table for the following statement. So, how would we make the truth table for P and not Q or not P? Take note class, it's now, there is a parenthesis there. So, make a truth table for the following statement, no? Yung P and not Q or not P. Our solution here is, first, we determine the number of rows required. Number of rows. So, since the statement contains two basic, no, only two, P and Q. We don't count the not P and the not Q. Okay? So, we have only P and Q. Therefore, the number of rows, the truth table will require 4 rows, or that's because 2 raised to 2 is 4. Now, to determine the number of columns required, there will be one column for each basic variable, and I would suggest also to put the negation, okay, so that it will be easy to look into. Then, the additional columns will be based on uh, the logical connective in the statement, okay? So, statement P or not Q, this means that we will have a total of 4 columns. Okay? So, this will be our possible columns. Okay? So, you have PQ, then not P, not Q. Then we have the P and not Q. Then after that, we have the P and not Q or the not P. Okay? Then you use the definition of the conjunction and the disjunction. All right. I hope you follow, ha? So a propositional form is an assertion which contains at least one propositional variable and may be generated, no, by the following rules. Okay. Now, we have to take note of this. A propositional variable standing alone is a propositional form. If P is a propositional form, then Q is also a propositional form. If P and Q are propositional forms, then P or Q, P and not P and Q, and P biconditional Q, or P if and only if Q, are propositional positions by themselves. No? They are propositional forms. Now, a string of symbols containing propositional variables, connectives, and parentheses is a propositional form. If and only if it can be obtained by infinitely many applications of the rules 1 and 2 and 3 above. Alright? Now, let's have additional definitions. No? Let X be a set of propositions. So we can assign a what? A truth assignment to X. No? We say X can be true or false. That assigns to each propositional variable a truth value. A truth assignment corresponds to one row of the truth table. Okay, so the other definition is we have a tautology. What's a tautology? Is a propositional form where every truth assignment is true. All entries of its truth table are true. No, we have the independent proposition, and we if we come up with a compound proposition, then we come up with all the truth value of all the possible rows are true, then you call it tautology. No, every truth assignment is true, so all entries of the truth table are true in the last column. Okay, while a contradiction or absurdity is a propositional form where every truth assignment is false. So when you construct a truth table and your last uh, column will generate a false, all false statement or false assignment, so it's a contradiction. While we have also what we call the contingency. Okay, what is this contingency? A contingency is a propositional form that is neither tautology nor a contradiction. So if it is not all true, if it is not all false, then it may be a contingency. Okay? Hope it's clearer. Okay. Now, example. P or not P is a tautology. I will show you using a truth table. P and not P is a contradiction. So P or not P is a tautology, while P and not P is a contradiction. After I will show you the truth table, I want you also to determine for each of the following compound propositions. Determine if it is a tautology, contradiction, or contingency. And therefore, you have to open your GCR. That will be part of your activity. Alright? But before you go further, let's continue with our lesson. Okay, so this is the truth table I made for you. So I see P or not P is a tautology. Why? You see, whatever the independent proposition here, but the new proposition generated is always true. P or not P, all true. No? So we call that P or not P is a tautology. While P and not P is a contradiction. No? You see, the independent the independent statement here, it's this is true, this is false, and this is false, this is true. But when we make the conjunction, it's all false. Therefore, it's a contradiction, or we call it a absurdity. It's a propositional form where every truth assignment is false. Okay? Now, so this is your activity class, huh? That's your activity. Okay, please proceed to your activity. Okay. Yes. Have you gone to your activity? Here's my answer. Okay. So, for each of the following compound propositions, determine if it is tautology, contradiction, or contingency. So, you are to construct the truth table for the compound propositions above. Go to your GCR. Okay. Now, let's continue with our new lesson. Definition. We call this the logically equivalent. No, logically equivalent propositional form have identical values for each assignment of the truth values to their component propositional values. So we can denote the logically equivalent variables P and Q as P double arrowhead Q, or we say P and only if Q, or P is logically equivalent to Q. So we say that's logically equivalent propositional form. Okay. So when do they have uh, true? If both P and Q are the same truth value. Okay. So let's have the example there. The square of x plus 2 and x squared plus 4x plus 4 are regarded as equivalent algebraic expressions. Okay. So show that P implies Q and not P or Q are logical equivalent forms. So we can use a truth table to show its uh, equivalence. No? So we have PQ. So we have P implies Q. So this is an implication in only false if the hypothesis is false and the premise is true. So this is false. Okay. So we have not P. We simply negate this. No? So true, true, false, false. Okay. Then we have the not P or not Q. So not P, this one, not P or Q. So it becomes also true, true, false, false. Try to see the truth value of the two. Are they equal? Yes, the truth assignments are the same. So we say P implies Q and not P or Q are logically equivalent propositional forms. In other words, P implies Q, you can write that also as not P or not Q. And what will be our evidence? We say they are logically equivalent propositional propositions. Okay, consider the following. Are they logically equivalent propositional propositions? Ah, not Q implies not P and Q or not P. Are they logically equivalent? Okay, try to see the truth table. Ah, So you have there not Q implies not P. Then you have the Q or not P. And we have also the P and not Q. So we try to, given the propositional forms Q or not P, not Q and not P, uh, Q or not Q implies not P, and not P and not Q. Between which pairs of these forms does the relational logical equivalence exist? Okay, looking into the truth table, this one have the same truth assignment. So therefore, they are logically equivalent. Okay. In fact, class, there are many logical equivalent uh, forms and therefore can be regarded as alternative expressions of a propositional propositions. So we say P implies Q and not P or Q are logically equivalent. So we can uh, represent them as an alternative. By the way, the following are logically logical equivalence, or they are logical identities, or there are rules of replacement. So P, if and only if P or P, so when you have B or P, that could be written simply as P. P and P, that can be written as P. We call that the idempotence. Then we have also their commutativity. P or Q, that is the same as Q or P. P and Q, that is the same as Q and P. They are logically equivalent, or they are rules of replacement. No? They can interchange. Okay. Associativity. So if you have three ors, so you can associate P or Q or R, or you can say P or then you combine the Q or R with a parenthesis. That is the same with conjunction. We have also the De Morgan's law. Okay? So yung the not of P or Q is the same as not P and not Q. In other words, class, when you negate an or, so we have a conjunction. When you negate a conjunction, that becomes a disjunction. Okay. De Morgan's law. Then we have also the distribution of or over an n. Okay. See how they are distributed. So P or Q and R, so we distribute P to both Q, then we have P, then R. And they are or but combined with an N. Yeah, we call that the distributivity of P over distributivity of or over an N. Okay. So we have also distributivity of N and or. Okay, so we have P and Q or R. So we distribute first P and Q. So we have there. Then an or P and R. Okay. Double negation. So P can be written as the not of P. We call that double negations. Then we have material implications, material equivalence, absurdity, contrapositive or transposition. And we have also what we call the exportation. Okay. Now, we need the following because we make our uh what's this? Our truth value. Instead we do truth value table, we can use logical identities to determine the truth value of the statement. Now we have additional identities here, no? We have P or 1, or when we say P or 1, this 1 is true, huh? So P or true, that is true. P and true, that's P. The not of false is of course true. So yung one here is actually true. Okay, you can just change it in your paper manually. Okay. Example class. We want to show that the biconditional of the negation of Q and P implies not Q. Uh, can you show whether this biconditional are true? So, or uh, are they logically equivalent? No? Are these two, no, logically equivalent? So we have the following solutions. So we say the not Q and P. So we start with the left. Can be written as not Q or not P. And that is De Morgan's law. Diba? We negate the conjunction. We have the not Q or not P. That's a conjunction. Then we can just what? We can just rearrange by commutativity because both are negative, both are negation. So it's an or. So we can simply say not P or not Q. That is commutativity. Then remember we have here a MI. What's MI? We call it the material implication. Oh, where P implies Q, we write that as the not of P or Q. Take note, P implies Q. We say the not of P or Q. Ah. So we say the not of P implies the not of uh, the not of P implies Q. So we have so the not of P is P implies not Q. That is material implication. Okay, that's how we show that these two are logically equivalent. We use the logical identities. Okay, this is another example. You can just read by it yourself. And we have the following basis as our solution. Okay, so next topic we shall discuss about argument. Okay, for now, that's all for the day. Thank you and good day. Bye bye. Please subscribe.